Compared to a normal chemical combustion, nuclear energy releases a lot more energy per gram. In fact, it works out to about 1,000,000 times more energy per kilogram as compared to a chemical reaction. If you're going to deal with moles, then the number of ratio difference is even higher. There's actually two different types of nuclear reactions: nuclear fission and nuclear fusion. With regards to fusion, that's fusing things together. So you start off with two separate nuclei, you push them hard together, you give it a lot of thermal energy and a lot of pressure. Before you know it, they'll snap together and turn into one entity. That's what happens on the sun. Maybe you remember learning that in grade 9 science, where you have a hydrogen nuclei, another hydrogen nuclei. With enough thermal excitation and pressure, they'll snap together and release bucket loads of energy and turn into a helium nucleus. What's been done that's been so much easier, at least for us as human beings, is the opposite of fusion, which is fission, which is a term coined from biology, where when Robert Hooke was observing the cells, he noticed that there were some cells that fissioned off into two separate cells. So it's the conversion between one entity into two separate entities, and that's nuclear fission. So you have one large nucleus, which is singular, separating into two smaller nuclei. That's been doable for many decades now. That's how nuclear power plants work. Of course, very recently we've been relatively successful with nuclear fusion, and eventually that detail will get into your textbooks, at least in high school textbooks. But for now, especially since your textbook is about 12 years old, that was a dream to become realized. With regards to our current technology, nuclear fission, it's rather predictable. Often we use uranium as our chosen substance for the fusion. It's an interesting reaction. You take the uranium and you flick it, and is it like as if it was a big giant Lego piece, it might crack in half. So that uranium, once you give it that initial energy excited by a neutron, it causes it to break apart into smaller parts and releasing more neutrons along the way. And if those neutrons are moving fast enough, often when you mine for uranium, you're not mining for one atom of uranium, you're mining for a small chunk of it. There are bajillions of other uraniums around, which those neutrons over here can collide with. And you can guess what kind of madness happens after that. It's known as a chain reaction. As for this formula over here, this is not the only type of nuclear reaction that can happen with regards to uranium. If you've ever broken Lego before, it doesn't always crack exactly the same way. There are many different ways how it can break apart, and that's true with regards to uranium as well. In fact, if you take a look on page 337 in your textbook, it shows you the various common daughter nuclei that are formed from this nuclear reaction. So for example, the uranium can break down into barium and krypton, or it could break down into niobium, or you're so broke that you got antimony. Yeah. And there are many other possibilities as well. For example, I don't think we covered this one yet, strontium and krypton, or even xenon. Xenon and strontium, or krypton and barium. Yeah, krypton and barium, or rubidium and cesium. So there's many different possibilities that may exist. So if you're wondering, well, which one should you be focusing on? Well, I'll just give you one specific example of it on any future quiz, test, or exam. An atomic bomb is one where the nuclear reaction is not regulated whatsoever. So any of those possibilities can come out of it, and there's a lot of nuclear fallout from such a reaction. Nuclear reactors are able to regulate this chemical reaction. Now, the isotopes that are formed over here, it's not to say that this is stable. Usually the daughter nuclei that are formed, they are still relatively radioactive, as they do want to decay into a more stable state. Here in Canada, we have a special type of nuclear reactor called a can-do reactor. Yeah, you can do. Can is obviously for Canada. Do is interesting because do is for a special type of water called deuterium. It's a water that's heavier than average water. That's why they call it heavy water. What makes heavy water so special? It has to do with the fact that the hydrogens are heavier than they normally are. In ordinary tap water, usually the hydrogen is isotope number 1. As for the oxygen itself, it will be element number 8, and it'll have an atomic mass of 16. This is known as the standard atomic notation, or the AZX notation. So you have the number of protons down below, and then you have the atomic mass written up above, followed by the element itself, or the element symbol itself. So this is an average molecule of water. As for heavy water, the hydrogens actually have a neutron in it. So normal hydrogens have 1 proton and 0 neutrons. That's why its atomic mass is still 1. But as for heavy water, the hydrogens have an extra neutron in them. So as for our nuclear power plants, we use deuterium. Why so? Because interestingly, deuterium is an excellent moderator of a nuclear reaction. So with regards to uranium, uranium can be properly regulated using deuterium. And if the reaction happens too fast, all they have to do is drop the deuterium, because once you drop it, now the now the neutrons move so quickly that they just simply zip and just pass right through the uranium without any side effects of it. It's kind of interesting. And that's in general what a nuclear power plant looks like inside. So you have the nuclear reaction happening inside the calandria, and here's the cartridge that's placed inside for the nuclear reaction. It releases tons of thermal energy, and our best way of converting heat energy into electricity is a very long-winded process. We don't have an efficient method for it yet. So that heat energy is then used to boil distilled water. All right, this is heavy water over here, so this is deuterium, often written down as D2O. It's used to heat up distilled H2O. And if you heat up distilled H2O to high enough temperatures, it begins to convert quickly into a gas, producing pressure. Now, with gases moving, now you form wind. And wind can be used to blow a fan. If it's a highly efficient fan that can convert a lot of that movement of air into spinning motion, it's known as a turbine. That spinning motion is used to take a motor, and as long as you spin a motor fast enough, you can generate electricity with it. But more on those fun details in the next unit. Until then, I have this cool little demo for you. Here I have a motor with LEDs attached to it, and as long as I spin the armature, you'll see that the LED lights up, just like so. And the other side will light up if I spin it the opposite way. So yes, the direction I spin the armature does change the outcome, and I'll leave that as a teaser for our next unit. Now, with regards to distilled water, it ain't cheap. They don't want to be manufacturing it non-stop just for this experiment over here. So they want to recapture it again. So what they're going to do is that they need to cool down the steam and convert it to water again. Where can they cool it down? Well, they can simply dump it. Often, if there's a large body of water around, they'll pump in that cool water, and that cool water can be used to convert the steam back into liquid again, where it goes through this crazy process. No, this process is not efficient whatsoever. There's a lot of mechanisms going on, but this is the best we currently got. Yes, there's this new type of technology called, I can't remember, you can Google it up. I know Peltier is the opposite of it, where you can have a hot and cold section on a surface, and as long as you heat up one side sufficiently, the other side, compared to the other side, it will generate energy. And what's that effect called? Oh, I should have looked it up beforehand. Do I have it on my cheat sheets? I can't read my writing. I had it written right down over here. You can Google it up. It's an interesting effect. All right, where with a solid state device, you can use a temperature difference to generate current electricity. If you've ever seen this before, this actually gives you a hint of where Springfield is at. I'll tell you this much. It's not near a big body of water, because if it did, they would use this technology. But since they don't have a big body of water nearby, they end up using these evaporating chambers, where they have the hot steam pass through these pipes, where by natural convection, the heated pipes cause cool air to be drawn up and pass through it. And then that's where the thermal energy is removed, and the water condenses, and it goes back into the nuclear power plant again to be converted to steam to spin the fancy fan called the turbine one more time. As for nuclear decay, it can happen naturally as well. It doesn't have to be forced like with regards to a nuclear fission or fusion reaction. However, when they decay, they often emit out some form of radiation. And let's just talk about the most common forms of nuclear decay. In grade 11, we usually talk about an alpha decay, a beta negative decay, and a gamma emission, as it's not a particle. Once again, as a reminder, an isotope is effectively a different flavor of vanilla ice cream. So you can have ordinary vanilla ice cream, you can have extra creamy vanilla ice cream, you can have my favorite, which is French vanilla ice cream, or you can get that cheap fake stuff. They call it vanilla dessert, I think, vanilla frozen dessert. And it's pretty creepy. I don't know if you guys ever bought that stuff before, but you take a dollop of it, put it in a plate, leave in your backyard for 3 hours, stare at the plate afterwards. It still looks like ice cream. It's creepy. Spend double the money. Get some real ice cream. All right, but an isotope is effectively the same exact thing, but you'll have lighter or heavier versions of it. For example, when we talked about water, you could have ordinary water, or you could have special heavy water, which, yes, 0.00 something, 1% of it is heavy water in here. And there's a method of extracting it, electrolysis if you want to look it up. So you can extract out heavy water from the regular water that we have. And there's a special type of hydrogen where it contains 2 neutrons inside its nuclei, or nucleus, and that's known as tritium. So there are different isotopes of hydrogen itself. Yes, you can do an experiment. If you take an ice cube made with heavy water and you freeze it, or water that's heavy water, you freeze it, that heavy water ice cube will sink. It won't float like normal. And of course, you're dropping it into tap water. And that's because heavy water is so heavy that even when you freeze it, the density is still greater than a tap water, so the ice cube will sink. It's a fun $60 trick if you got $60 to burn to purchase that much heavy water. In fact, yeah, I'll share with you this joke over here because it's important for what we got to do. A biologist, a physicist, and a mathematician were sitting in a street cafe watching a crowd. Across the street, they saw a man and a woman enter in another building. 10 minutes later, they appeared together with a third person. Ooh. They have multiplied, said the biologist. Oh no, an error in measurement, the physicist sighed. Well, if exactly one person enters in the building now, it'll be empty again, the mathematician concluded. Hope you get the joke. I know it sounds weird, but this is what we gotta keep in mind when we're doing this whole balancing equations. The math just has to work out, even though it seems impossible. Once upon a time, scientists didn't know what an alpha particle was. They just knew that there are certain substances that emitted off radiation, and they could see the radiation because the invisible stream that comes out of it, when it hits a plate that's covered in phosphorus, it would cause it to glow. And they coined that unknown substance as an alpha particle. Today we understand the alpha particle is actually the nucleus of a helium. So helium, He, it has 2 protons and 2 neutrons, giving a total mass of 4, but because it's missing its electrons, it has a charge of +2. Radium does naturally decay into a new substance and release off an alpha particle. And once again, we need to follow these 2 rules here. First off, the atomic mass must balance out. So if we start off with 226, it must add up to 226 on the other side. 4 have been given away to helium, so 226 subtract 4 gives you 222. And the atomic numbers must add up. So you start off with 88, you got 2 over here, 2 plus 86 will give you 88. So with regards to a large radium nucleus, isotope number 226, it's unstable. Over time, in order for it to cool and chillax, it needs to give off something, and it ends up giving off an alpha particle. In doing so, it becomes slightly lighter, and if you recall back in chemistry class, elements are defined by the number of protons. So if it lost 2 protons, now it's become a brand new element. All right, so effectively, alchemy does exist in the form of decays, nuclear decays. So you look it up on the periodic table. What element is number 86? And that turns out to be radon. Once upon a time, they used radium on the bezels, not on the bezels, on the dials of watches because radium does a really good job of glowing in the dark. Berkelium-248. Let's say that is the daughter nuclei from a decay. In other words, after reaction, now you see that you have berkelium. Well, what was the original parent nuclei? What was it before the alpha decay? I'll let you guys work that out. First off, keep in mind an alpha decay, it has an atomic mass of 4 and 2 protons. So if you have 97 in the center afterwards, you had 2 more inside, so you start off with 99 protons. 248 is an atomic mass afterwards. It was 4 more atomic masses heavier, so you start off at 252. Which element is that? Thanks, Einsteinium. Here's another variation of an emission. In this case over here, interestingly enough, you upgrade on the periodic table. Somehow you end up increasing the number of protons. And what's happening is that a neutron is losing its negative portion and it suddenly becomes positively charged. Very strange. And these emissions, they travel near the speed of light. As they are rather large, because they have mass and occupy space, because it is an electron, it eventually can be stopped by something. In this case over here, aluminum. All right, I did mention that this is an upgrade on the periodic table, so let's go through this. Let's say that you have tritium. All right, and in the tritium nucleus, let's say that one of the neutrons ends up losing its neutral charge because it loses an electron or loses a negative portion of its charge. Suddenly it becomes positively charged, so now you have something that has effectively 2 protons in it. However, it's 2 protons and 1 neutron. Remember, it was just one of the neutrons that has changed into a proton. So the atomic mass still remained relatively the same. So still 3 to 2. What element's number 2? That's right, helium. Super unstable, super freaky. Try out this one. You might have heard of carbon-14 before. We'll talk more about that in the next episode. It is used in carbon dating. So, carbon-14, if it decays, what does it turn into? Have you worked it out? Once again, you just simply upgrade in your number of protons. Atomic mass remains relatively the same, and you have nitrogen. Before I move on, often when they write this out, it just has to abide by the weird, awkward joke. The math just has to work out. So hopefully you appreciate this joke better now. It doesn't make any sense according to the mathematician, but the math has to work out that way. And that's what we're doing here as well. All right, so as for the electron, we're not talking about its atomic mass down here. It's just the only way for the math to work out properly. They have to put a -1 there so that logically -1 plus 2 gives you 1. So the math can work out in all these cases. As for a gamma emission, it's one of the most highest intensity electromagnetic radiation that we have detected so far. And it's pretty much massless. It's just high energy. As a result, that's why we write down the formula like this: 0, 0, and we just use the Greek letter gamma. So write an equation that represents a cesium-137 from a nuclear fallout that then emits both a beta negative emission as well as a lot of gamma radiation. In the formula, all you need to do is just simply tag gamma down at the end. That's all you need to do, as it's not going to impact your formula. It's more of a reminder to tell the reader that this is being omitted during this reaction. Again, the math has to work out, so 56 subtract 1 will give you 55. Element 56 is, excellent, barium. Now you know. With all this newfound information, most of your homework is just on fill in the blanks. So if you need to watch the video and read through the little scripts again, by all means. Catch you later.